So in this example, the work done and consequently the stored strain energy, which we're going to use the letter capital U for strain energy, is the integral of F du. And there's no cosines in here because the F is in line with the U. So F is equal to K times U, and we have K out of the integral, and we're left with U, so we have U squared over 2, so we have KD squared over 2. So F is equal to K times D, D being our final displacement. So D is equal to F over K, and we have capital U is K over 2 times F over K, that quantity squared. So we have U is equal to F times D over 2. And it confirms this idea of the integral being a triangle for a linearly increasing load, the area of the triangle. And here's one of the pictures that you've probably seen in some form in your structural analysis class when you did talk about virtual work. So we have the shaded triangle in here being what we just found, 1/2 the base, which is the distance d here. You can see the capital D times the height. Height is F. So that's our shaded triangle. It's 1/2 the base times the height. The white triangle is the complementary strain energy, and that could be 1/2 the base times the height here, and D we just found was F over K, so I could swap in F over K, so 1/2 F over K, so I could express the complementary strain energy in terms of the force. So notice what I did here. I have the strain energy expressed in terms of the displacement here, and the complementary strain energy expressed in terms of the force. Displacement and force. So the asterisk reminds us that it's complementary, and clearly something cool is going to happen, and what it is that if the F versus U relationship is a straight line, it's very, very obvious that the white triangle is the same area as the shaded triangle, so U is equal to U star. And I don't know if that stunned you or not. It probably didn't, but it has very, very deep implications. In fact, so deep that I'm sure your head will hurt at the end of the lesson. Okay, let's take it one more step here and let's talk about virtual work. Again, it's a term that you've seen before. I don't know if anybody really understands it, but let's take a stab at it. A virtual displacement is an imaginary thing. It doesn't exist. That's why it's called virtual. And it's very, very small. And it happens in the equilibrium configuration here. So that's a key idea, that when after the loads are applied, you're in equilibrium. So for instance, after the F has been applied and we're stretched to D, then we apply a virtual or a very, very tiny imaginary displacement. So the virtual work is the work done by all of the forces, and this is probably the hardest part of it. I'm going to underline this here. All of the forces, both the internal and external, during that virtual displacement. But most importantly, what's going to happen here is when we have that virtual displacement, this original force wiggles with that displacement. That's the hardest part to kind of get your head around here. The work done by the internal forces due to these small variational changes is equal in magnitude but opposite in sign to the change in strain energy, which we just looked at. So that's why we focused on U.